This video clip is for a MATLAB Simulink Simscape term project report presentation. My name is Nanam Ploy. Let's begin with the cruise controls. The car mass M is 1.1 times 1000, which equals to 1100 kilograms. The damping is 0.9 times 50, which equals to 45 Newton seconds per meter. And the reference speed is 12 meters per second. I made two models, a Simscape model and a transfer function model. After that, I tested both modules by giving a step input. The outputs from Simscape and transfer function were similar, so my model seems to be corrected. And here I use the best cases for two gains to get the reference speed. Gain 1 I set to 5 and gain 2 I set to 1 over 1.08. Next, I designed the P controller. As you can see, for the step response for this P controller, it improved the speed a little bit but has steady state errors. And for the root locus, the P controller moves the poles left a bit but not much improvement. And for the board diagram, it gave small gain and phase margins, so the system was not very robust. For PD controller, the step response made the system faster but still had some steady state errors. And for the root locus, it added a 0, which made the root locus move left, making the system faster. And for board diagram, the controller increases the phase margin, making the system more stable. For PI controller, the controller removed the steady state error but made the system slower. For root locus, the controller added a hole near a 0, which improved stability a bit. And for the board diagram, the controller had low frequencies gain but was still weak at higher frequencies. The last controller is PID controller. For the step response, which is this one, the PID controller gave the best result with fast response and no steady state error. For root locus, it gave the best root locus, and for the board diagram, the control had the best overall minimum on both gain and phase, meaning that the system can handle more disturbance. In short, PID controller gave the best performance in time domain. It made the cruise control system fast, stable, and strong against disturbance. Moving on to part 2, motor speed. The motor parameters according to the table are the J value equals to 1.2 and the B values equal to 1, KE equals to 0.8, and inductance L equals to 1. Here are the two models, the Simscape model and the transfer function model. Then I compare the outputs, and this is the results. And I tuned these two values to get the a better response for the requirements. So J equals to 0.3 and KG equals to 5. For the P controller, in step response, it made the motor faster, but there was still some steady state error. In root locus, it slightly shifted the poles left, and for both diagram, the controller gave small phase margin. For PI controller, the step response for the PI controller, the step response removed the steady state error but made the response slower in root locus. It added a pole at the origin, which improved stability a bit, and for the board diagram, the controller improved low frequency gain and better tracking. For PD controller, in step response, it made the system faster with an overshoot, and in root locus, it shifted the poles left quickly making a faster system, and in both diagram, the controller improved and the phase margin better for fast response. Lastly, the PID controller for step response P was the best with a fast rise time, no overshoot, and no steady state error. In root locus, it gave a good balance to both. It made good balance and became more stable. And in both diagram, the PID controller gave the highest phase and gain margins, making the motor system very strong and stable. Next, part 3, motor position. The parameters according to the table are JP equals to 1.2, BP equals to 1, KB equals to 0.8, LP equals to 0.8. And the last two parameters according to the site are RP equals to 4 and K equals to 0.0274. Now these two models, which are SimScape model and transfer function model, shows movement and transfer function matching the equations. And for the best cases, I adjusted the gain inputs to 15 and gain feedback to 1 over 2.5 to get the best response. And here's the graph. For the P controller, the step response improves the speed but still has steady state error. For root locus, it shifted the pole slightly, and for both diagram, it has low phase margin. For PI controller, for step response, the controller removes steady state error but slows down the rise time in root locus. It improves system stability by adding an integrator, and in both diagram, PI controller has better low frequency tracking. For PD controller for step response, it made the response faster with small steady state error. It still remains. In root locus, it made the pulse move left faster, and in both diagram, it has better phase margin. Last but not least, the PID controller. It again gave the best performance with fast rise time and no steady state error. But as you can tell, the settling time for these four controllers do not meet the required set, which is to be less than 0.1. In the control menu, I could not tune any controller to make the setting time to be less than 0.1. This is because the system has high inertia. It reacts slowly by nature. The system also has high electrical resistance of 4 and inductance of 0.8. It slows down the electrical dynamics in control system design, and in root locus, the branches move slowly left, but not enough to make sudden time under 0.1 second. In both diagrams, we can also see low bandwidth, which limits the speed of response. Last but not least, part 4, aircraft pitch. The parameters are A equals to 1, B equals to 1, and C equals to 1.2. Now, because of the CTMS website error, I could not obtain a SimScape model, so I will use a transfer function model instead. For P controller, it improves speed slightly, but the steady state error still remains. In root locus, small shift and pause, and for import diagram, we have a small margins. For PI controller for step response, it removed steady state error but made the response slower. In root locus, it added a pole at 0, which improves stability, and in both diagram there is better low frequency gain. For PD controller, it may respond faster, but slight error still existed in root locus. It made the pulse shift left more, and in both diagram, uh, the PI control the PI controller has better low frequency gain. For PID controller, it was the best with fast rise time and no steady state error. In root locus, it shows the best pulse position for stability and board diagram. It gave the highest margin, making the aircraft pitch control system very stable. Overall, PID control again give the best control. To summarize, in all four systems, uh, cruise control, model speed, model position, and aircraft pitch, the PID controller gives the best results. The controller made the system fast, stable, and good at handling. This concludes the report. Thank you for your attention.